Okay, guys. So welcome to another lecture in Physics 102, and we are going to finish the business of light today, and we are going to continue talking about the reflection and refraction. Okay, last time, I think the main one that we pretty much like had to deal with, like mathematically, it's going to be this Snail's law right here. Okay, this is the one that we are going to use pretty much everywhere, every time that's light is trying to go from one medium to the other medium, and they having this different sort of like properties. That means we use this, the refractive index or index of refraction, to describe how fast that the light can travel in that medium. So if we can calculate the speed of light in that medium, and then we take that number, and then we started by taking the speed of light in vacuum, which is the pretty much the ultimate speed in our universe right there. And then we just divide that by the speed of light in that medium. And we already talked about it, that this ratio is always larger than 1 as long as it's not a vacuum. Okay. So with that, then you plug it in into this equation right here. And then you have the incident angle. Oh, what is going on with this PDF file here? Okay. The incident angle and refracted angle. So Snail's law just saying that the product between n and the sine of the angle must stay fixed, right? When it's trying to go through mediums there. Okay, sounds cool. All right, so what we can do today is just to do a couple more exercises just to make sure that you understand how things go. But before we get to that, I think I would like to show you once again the simulation that will help a lot, and it's still the same simulations website that you used before. So what I'm gonna do is I'm gonna switch. Oh, let me actually copy that website so you can check this out. All right, it's still the allphysics.com, and then I'm just going to pick different simulation to show you. Okay, so it's right there. Okay, here we go. So what you can see over here is I just pick the one that is showing you about the reflection and refraction. And as I just like the previous simulation, and you can see that if you look at the menus up here, there are a lot of simulation that you can use to help you understand more of the material that we are discussing right now. So what we have over here for you is just the refraction. I think I have to adjust the incident angle using this slider over here, as you can see. All right, so what I can do is I can adjust the index of refraction n on the upper portion of the medium and the bottom portion of the medium. And as you can see, if I set the upper one to be 1 and then the below, it could be like super big, like let me set n2 to be like 2 something. So we already understand the, the behavior of the light. The lights will come in with the incident angle, in this case, like some number 56.3, and then the bend refracted ray will bend toward the normal. So as you can see, the refracted angle is going to be smaller than the incident one. See? All right, so that's cool. That is cool. So that's what happens is when you change the incident angle, the refracted angle will change along with it. No problem. Okay. And then when you look on the right side of this one, as you can see, we discussed briefly about this one is every time that's the light trying to go from one medium to different mediums, there will be a fraction of that waves gets reflected all the time. And that's the faint light coming out on top there. That is your reflection. All right. So actually you can let this one go. So you sort of like don't distract you in terms of like if you are going to focus only on the refraction. But in reality, there'll be part of it get reflected back all the time. Okay, cool. All right. Now, and I think this simulation is kind of nice that you can actually have like some sort of like a deviance, sort of like the path or the line that's showing you the deviation from the original path. All right. And that will give you some idea of how things get refracted when it's trying to go through the interface. Okay, is that cool? All right. So the crucial phenomena that we studied last time is when we go backward. So that means if I increase the upper medium and then I try to lower the lower, here we go. So let me start from 0 angle here. So let me switch sort of like the value of the ends. So now the upper portion has a larger n equal to about 2.1, and below is n is 1.5. And as you can see, I start the incident angle at 0. So the light just sort of like go through. There's nothing new here. And now once you start increasing the incident angle, so I'm just gonna go like this. Yeah, you guys see that? Okay, very cool. So what you have over here is now the refracted ray will bend away from the normal, right? Because now you're coming from the larger value of n to a lower one. All right, and so I'll keep increasing, keep increasing. Okay, I think I can get rid of that angle, and actually you don't have to worry about the refracted. Oh, actually that's kind of nice to have. Okay, here we go. So just keep increasing the incident angle. Now refracted angle will get even larger and larger and larger and larger until eventually you can see that around here somewhere, when your refracted angle approaching 90 degree, that's when you're about to hit the critical angle. Okay.
Okay.
And that's what happens afterwards. When you increase even more, now you are going to get total internal reflection. As you can see, now there will be no more refraction get into the second medium anymore. And that's, I mean, you have to do a fine calculation there. I mean, the slider doesn't seem to do it. All right, here we go. All right. Oh, I can just tap on it and just change by 1. That's nice. Okay. All right. So here we go. So that's what it is. Right. It's still not there. Not there. Not there. Somewhere. All right. Somewhere. There you go. All right, it's popping up right there. So somewhere around here, about 45.6 degree, that is your critical angle. So if I go a little bit lower than that, now I still have some refraction get into the second medium. And if I go just beyond that, then there'll be nothing. It's gonna be perfectly like 100% reflected. Okay, sounds good. All right, so I hope you having sort of like a good time. Play around with this simulation. And actually, well, I forgot to use this one at the time that we did the interference. So if possible, you can go back and look at there is the interference here as well. Even though we study interference in sound, however, as I said, it works with any kind of wave. So this one is it's a light wave, but as you can see, you can imagine this is going to be just any kind of waves. It doesn't have to be light. And as you can see, if I get rid of the wavefront, this is exactly the problem that we saw before when we, okay, let me increase the size a little bit here so it's easier for you guys to see. So over here, as you can see, now that will allow you to sort of like compare with the problems that we did before that when we're standing at the center. Remember when you have two speakers and sending out the same type of waves, and then you're standing at the center, and that will be your constructive interference. And then you just move up, 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 up. And then if I show you the wavefront, okay, the maxima is right there. The line, the dashed line there, that's the location of the maxima. So that's the location of the constructive interference. So that's why you're standing at 0.0 over here, and then you have like a loud sound. And then when you walk up, 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 it's gonna go quiet in the middle. And then eventually it's coming back and loud again at the point of that dashed line there. And then it's going to have the alternative between loud, quiet, loud, quiet, loud, and quiet, on and on. Right. So I can show you the wavefront over here. That's what happens. Okay. So at the crossing point, that's the one that you get the constructive interference. Is that cool? All right. So I hope this might help a little bit in terms of like if you want to dig a little bit deeper into the geometry of the problems, and this will help a lot. And also you have the even the simpler one if you want to. So this is a simplified version of that. That was like the whole scenario of what is going on the space around those two sources. And this one is just like particularly talking about one particular problems, and this one one particular setup and at one particular point. So this one is exactly the same as the problem that we saw once again in class, and this one has a better animation. So I should have popped this one up like while we were doing that one, so you have a like a comparison at that time. But this is what it is. Okay, so you can see that this simulation is kind of nice because that allows you to adjust once again the wavelength. See, and now you will have a chance to take a look at the point of interference. That is it going to sort of like match perfectly or not? If they're not, then that means you're not going to get either destructive interference or constructive interference, on and on and on. All right. So for you to be able to like match perfectly, you have to play around with the wavelength, or you just have to go to different places. Like, yeah, I'm going to change the Y. You just have to play with it. And as you can see, they have the dots for you. That dot will mark the crest of the rate of the wave, or you can put the trough of the wave, depends. All right. You want to put the dot there just to make sure that you know which position you're talking about. And for you to have a constructive interference, those two dots has to meet at the point of interference exactly at the same time. So that's why you have to just like, okay, I'm keep finding it. That's, I mean, you just go back and try to play this one. It's fun. See, as you can see, the black dot doesn't hit me at the point of the tip of the arrow at the same time. So that means I'm not going to get like perfect construction or perfect destruction over there. Construction, perfect constructive interference or destructive interference. Exactly. I still have to keep moving somewhere. Okay. So just adjusting this until I get to the point almost there. There you go. Almost. There you go. Pretty much. Okay. I hope you can see it. Let me pick another point there. Down here. Now, there you go. Almost there. And of course, you can expect that if you right in the middle, you're going to get a constructive interference anyway. All right. And then you just move up a little bit. All right. Find it. Try to find it. All right. It seems like I'm having fun alone over here. All right. But I think I know you know how to play this one right here. All right. So almost there. There you go. I think maybe that's pretty close. Okay. So right there. Oh, maybe like my face is in the way or not. There you go. All right. Here we go. There. As you can see, the black dot just hit the point of the location that we try to detect the oscillation exactly. So this is going to give you the constructive interference, something like that. So I don't know would this help or not, but I found this website and simulations to be very useful. And because it's animation, it works perfectly with the waves and everything. Yeah. Okay, guys. So sort of like if you have time, just check it out. I think it's pretty good. All right, guys. So let's come back to our lecture right here. There you go. All right, let me switch back. All right, so back to our business over here, guys. So I hope this helped a little bit, but don't forget to check them out. There are so many simulations. I think the libraries of simulations is grow over time since last time I checked. So I think they put sort of like a couple more or maybe a lot more in the waves and light. And they also have some mechanics and all the fun stuff there. Okay, guys, so let's come back and take a look at our exercise right here. So we are going to look at in the figure, you have a layer of light is perpendicular to the face AB of a glass prism, which given the index of refraction in 1.5. Find the largest value of the angle phi so that the ray is totally reflected at face AC. So you want the light to actually not getting through the face AC. You want it to reflect it back. So if the prism is immersed in air, well, this is cool. So let's look at this one. So part A. So what happened when this prism is just in air? So first thing first, what happened at the first interface? What do you think? Of course, look at this one. The light just hit the surface AB perpendicularly. So that means your incident angle is 0. You guys with me? Right? Because you're just going along with the normal line. So that means when you have 0 incident angle, so you're going to get nothing. It's just going to go straight out. Does that make sense, guys? Cool. So this perfect. So the first interface doesn't really give you any problems there. Now, when you hit the AAC interface, then you're going to start to have some refraction there. So first thing first, I'm just going to draw a normal line right there. That's a black line there. And now I can assign. So let me do just a regular angle over here. Let me call this angle theta. All right, because the apex angle of the triangle that's given to be phi. So I think I'm safe to use theta over here. And then, of course, you can expect that you're going to get the refraction out of this. And because you come from bigger n to a smaller n or whatever, but I mean, you can just draw any value to it. So something like that. Oh, let me change the color there. So let me do the red there. So it's going to come out in some different angle. So I can call this angle alpha if you like. Okay, so this is a regular condition, but for our condition over here in this problem, they said, hey, I don't want anything to get through the surface AC. They want the total internal reflection to start happening. So that's the whole trick. So what you have over here is in this particular problem is you don't have to do anything else except you just assume that the outgoing ray is going to be 90 degrees. That's what you expect. With me? Because this is going to be the crossing line between you are going to get refraction or not. All you have to do is just set the refracted beam to make a 90-degree angle with the normal. And then you go ahead, apply Snell's law at a point of refraction. So you can call this point P, for example. So let's say at P, so you say N prism, because that's where you're starting from right there. That's N prism there. And then you do the sine of the theta. That's your incident angle. Must be equal to the, now you come out in the air. So that will be in air. And then you do the sine 90 degree. So it's exactly the formula that you use to derive the critical angle. Sounds cool? All right. And that's it. So you should be able to figure out the angle of the phi, the requirements. The reason is because, of course, when you look at this one, this must be phi as well. So that means the theta is going to be 90 degree minus phi. So that's no problem. That allow you to write N prism. Okay, let me substitute the numbers in there. 1.5, and then you can turn theta into 90 minus phi. Put them in, put this term in the form of the phi. In air is 1, sine 90 is 1, and that's it. So you can say sine 90 minus phi is just cosine. So it's a cosine phi equal to 101.5. You can write it as like 2/3, and then you should be able to figure out what should be the phi value. Cool? And that is done.
Okay.
All right. So what happens if you look at the part B, they say, hey, I want this to immerse in water. Okay. So if that is the case, I put water. Let's do blue. So what happens if I just dump this in the water? There you go. All right. So that will be water environment around this. So the only thing that's going to get changed is going to be this. With me, guys? Because now the second medium that the light is trying to escape from the prism is not air anymore, but it's the water. So the only thing that you need to replace is in and water at the position of the in air. That's it. So part B, it will look exactly the same. So at same point, so you're going to get the same equation there. So in prism, sine theta equal to in water, but you still keep the refracted ray to be at 90 degrees. That's it, guys. So now you turn sine theta into cosine phi. In water, you can look it up in the table. It's, let's say, about 1.33. And then you have in prism to be 1.5. And then you should be able to figure out phi for this case, on and on and on. Okay, cool?
Okay.
And that's done. Not too bad. Okay, let's try again. So this one, I think this is like a warm-up question here. So you can do a more acrobatic question, but it's still under Snail's law anyway. I mean, we have only one equation to use. So try this one, guys. All right. It's kind of, I think the question in the exam will be somewhere around here. I would say the complicated problems that you might see in the textbook or in any problems or whatever, that's pretty much like the problem about the geometry. So it's just pretty much like send the light into some weird shape, you know, maybe like a dome shape glass, or you put it in like a, I don't know, like a triangular prism like you saw it before, or you put it in like, you know, like some block of some shape at some weird angle and try to find something. All right. So the difficulty is pretty much more like in the geometry, but not in the equation that you're going to use, because we have only one equation to use. It's Snail's law. Okay. In the figure, a light ray enters a glass slab at point A, and with the incident angle theta1 to be 45 degrees. And then it undergoes total internal reflection at point B. All right. So that's given already there. So, all right, it is a reflection. It doesn't say, okay, that's fine. All right, we can throw away the reflection. The partial reflection is always there. What minimum value for the index of refraction of the glass can be inferred from this information? So what you can see is at the minimum, what should be the value of the end of this glass for you to get the total internal reflection at point B? All right, so it's just sure. If you're just like increasing the end of the glass, I mean, the condition for the total internal reflection will get easier and easier. Does that make sense? Like you think about it, it's like if this is like a piece of diamond, then we already discussed that the total in the critical angle for the diamond air pair is going to be super small. So it's easier for you to hit the total internal reflection condition. Cool. So that's why we just say, okay, just give me the minimum requirement for the end of this glass for you to get the total internal reflection. Okay, what would that be, guys? So the idea is simple once again. So when you want to do something total internal reflection, you are talking about the bound, I mean, sort of like the borderline between you're going to get total, you know, total internal reflection or not. So that means you're going to set your refracted ray to be at 90 degrees. That's pretty much the whole key point. Yeah, you just set that. That will be the key factor that is going to go beyond or is still under the refractive condition. Okay, and then now I'm just going to work through the point of contact there. You can start from A if you like, start from the top. So that means, okay, let me write down the angle of the refracted ray down here to be alpha. So you can say at A, you start from the top is in air. All right, you start to feel this one now, yeah? And then you do sine of the theta1. All right, you start from the first medium there. Now you move into the glass. You can write it as in glass, and then you put the sine alpha there. All right, so you can plug in the number if you like. In air is 1, sine theta1 is 45 degrees. In glass, that's what you want to figure out. And alpha, that's unknown. So you can keep this as like equation number 1. And definitely we're going to need one more equation because now we have 2 unknowns. So let's take a look at point B down here. So now, once again, at the point of refraction, you do the Snail's law one more time. All right, now your incoming has a different angle now, but because now you can see this one is just a right triangle down here. So if the refracted angle is already given to be alpha, so what should be down here, guys? Of course, it's going to be 90 minus alpha, right? Okay.
Okay.
Right, they are related. So what I can do is at B, you can start from the glass first. So you can do in glass, sine 90 minus alpha. Cool. And now you move on to the air on the left surface. There is in air. And now you times sine, you already set it to be 90 degrees. And you are good.
Okay.
All right, now you can start substituting the value into it. In glass is still unknown. Okay, I just used just only G. I think that's good enough. Sorry, this is a little bit too long. Here you go. All right, in glass, and then you multiply by sine 90 minus alpha. You can turn it into cosine alpha. In air is 1. Sine 90 is also 1. Now you can take this one to be your second equation. Now the only thing left for you is just figure this out, and you are done.
Okay.
Okay. There are 2 things that you can do. If you have calculator nearby, maybe the easiest way is just take the ratio between these two. So it just take 1 divided by equation number 2. What you're going to get is going to get 10 alpha. You guys with me? Because the n glass will cancel each other out. So you're going to get 10 alpha. Okay, just to make sure that everyone follows here, I just say n glass sine alpha over n glass cosine alpha is going to be equal to sine 45. You can put like 1 over root 2 or root 2 over 2. That's up to you. Same thing over here. So it's going to be equal to root 2 over 2 divided by 1. Cool. All right. And this whole thing on the left turns out to be your 10 alpha is root 2 over 2. And from here, you should be able to figure out alpha using calculator. And once you get the alpha, then all you have to do is just plug in the alpha into one of these two equations to figure out what should be the n class. And that's it. You are done.
Okay.
Not bad, yeah? Okay. The other techniques that for those of you that sort of like love doing trigonometry back in the day, you can eliminate sine alpha and cosine alpha right away by doing the sine square plus cosine square alpha equal to 1 if you want. Okay, but you're going to pop out the n glass right away. So, but you have to square this whole equation, but it will work. All right, does that make sense? All right, so if you want to jump right into the n glass without doing the calculator, you just do the sine square plus cosine square equal to 1, and then you can eliminate the alpha from these two equations, and then you're good to go. All right, guys, so that's pretty much give you a good idea of what kind of question that will show up in the exam as well. It's going to be somewhere around here. I don't think there's going to be much more out of this. All right, is that nice? Oh, okay, very good. Question about light. Go ahead. What? Oh, I think you're typing. Just wait for the question a little bit. Oh, that's going to be a long question, looks like. Okay, when light passes through air, does it heat up the air? Oh, that's a good question. I would say, well, it really depends. When you say heat up, okay, so I have to think along with me a little bit, all right? So things gonna get heated. We already learned thermodynamics. That means it's gonna have to receive some energy. Does that make sense? So that means the only way that light can heat up the air, it means the air must absorb that light. So it takes the energy from the light. So that's how the air can warm up. Okay. However, there might be the case that the light might not want to interact with the air. When I say not interact, mean it might not fit the condition that they love to interact with each other. So the light just pass through the air. In that case, so air won't heat up. So I'll give you one quick example, and I think that will sort of clear things up a little bit. Thinking about microwave, the microwave oven that you use in your kitchen. Actually, the microwave is another kind of electromagnetic wave. So it's no different than light. It's just different wavelength. So the microwave can heat up your food because the microwave wavelength just match perfectly at the energy level that the water in your food can absorb that energy. So does that help? So that's why if you bring in some like ceramic and all the stuff into the microwave oven and then you just turn it on, that you can see that the if you put the good stuff in there, that's like a microwave compatible things, that thing won't heat up a lot. So that's because the microwave just pass through, and then you don't have a lot of like energy absorbed by that container or whatever, the ceramic stuff. Okay, good. I hope that helps. But that's a very good question, actually. And the underlying condition for that absorption is going to happen or not, actually, you need like some, to be able to sort of like look into it in fine detail, you need quantum physics there. Because the quantum physics will talk about the interaction between the electric field and magnetic field and all the photons and everything that happens there and the material. And that will give you the condition when and where things going to get absorbed, when and where things won't get absorbed, something like that. All right, cool. Thanks for the question. All right, move on to the next one. All right, so the last thing that we are going to do in this module right here is the formation of images, okay? And what we are going to do here is just take a look at what happens when light, after either reflection or refraction, eventually they has a tendency of getting into a focal point. When you say focal point, it means those rays of light could have a potential that it might just cut and cross at a single point. So if that is possible, then that means you can pretty much like replicate whatever the light that came out. And that's when the image is being formed. So think about this one, for example. So this one is pretty close to what you have in your digital camera. It doesn't have the digital, but it's been in your camera. So you have an object, you have like a lens system and other stuff, but eventually you can pretty much give the light source that coming out from your object. Eventually they will just, go through your system and eventually come back into the single point. So this means it's like you can copy that point on the left to the right. Does that make sense? All right.
Okay.
And that means that's how you can generate the image of that one, because you can take like a copy of every point on this, all right? And then those points will just pop up here, around here. So you can pretty much like regenerate what is on the object side into the image side. And this is called image formation. So by having this crossing point of the ray is so important because of this, this reason right here, because you want to pretty much like replicate every single point on the object into every single point on the image. And that's when you can generate the image right there. So this is why we are sort of like focused so much on where are the focal points, the point of concentration of those rays. Does that make sense? Okay. So that's what it is. However, to starting things out here, there are two types of images that you are going to have to deal with. The other type is the one that you familiar with. You look at yourself in the mirror. You see yourself in the mirror. However, that image of yours cannot be done anything with. It's like, I cannot touch it. I cannot bring my hand and grab it. I cannot put it in my digital CCD stuff to capture it. I mean, I cannot do anything with it. Okay, so the image behind the mirror that you are seeing in the bathroom or the stuff, that's not the real image. Does that make sense? The one on top that you just saw over here, that's real, because you can say that I can put this light on a CCD, on a film, on a screen, on a paper, whatever. That's real. The image is real. But down here, the image that you can observe is just by looking at by your eyes. You can only see it, but you cannot put the image of yours on the in the mirror into like a protect not protected, like a screen or anything. So we're gonna have that thing to be called the virtual image. Does that make sense? So there are two classes or two types of images that you have to deal with. The one that actually came from the actual overlap or the actual crossing of those rays, you're going to call them real images. And the one that you don't have, however, you can use the sort of like an extrapolation, you can extend the ray. The reason that we can use the extension of the ray is because this is how your eyes works. So look at this one, guys. So if there is a ray that come and hit your eyes, but that ray is actually diverging, as you can see that, yeah, the ray is actually diverging. Once it hits your eyes always interpret that the light hit the eyes in the straight manner all the time. That's where your brain has been trained, or I don't know where the brain is trained, but that's how your senses and everything is being functioned. So when you have the light that actually diverging, your eyes and along with your brain and all the system will interpret that, hey, the source must be coming from the direction that is straight out. Does that make sense? So your eyes will perceive that actually whatever you're seeing, it's come from this light source over here. However, this light source is not real because you extrapolate your rays by yourself. So that's why we call this a virtual one. Okay, that's conclude
Okay.
the difference between the real and the virtual image. In conclusion, the real image come from the real intersections between light rays. The virtual one, they are not. Okay, I mean, all those virtual images are from your extrapolation. You have to trace your light by yourself. The actual crossing of those rays coming from somewhere else, not directly into your eyes. Cool. All right. So once we classified two types of images here, now we're going to look at a very simple way of analyzing the position of the image formation, because we want to know where is your image. Yeah, even though, all right, the image is kind of like very easy to calculate in the plane mirror. When you have just a plane mirror, it's simple because you look at yourself in the mirror all the time. Whatever you're standing in front of the mirror, let's say the distance is P, you can tell your image is exactly the same distance behind the mirror. The P that we're going to use here is going to represent the object distance. The I that's we are going to use to represent the image distance. Sounds good? All right, but for the mirror, just a plain mirror like this, what you have over here is P is going to be equal to I. That's simple, okay? So we're gonna say the image distance is gonna be the same as the object distance. The reason for the same is because you're doing nothing. Everything just came from the law of reflection. So the way that you can trace the light to get to the location of the image is easy now. Actually, the light will just come out in all direction, right? Everywhere, 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 everywhere. Crazy, right? And once it hit the mirror, it will go reflection, reflection, reflection. All right. I mean, just try to draw to make it like a big mess over here, just so to represent that light just come out in all direction. But of course, what you only need just two. When they say just two means, okay, you can imagine that, hey, Ajahn, I just need like ray number 1 here and ray number 2. I think that's good enough, because once I just catch these two rays, I know the behavior of the whole thing. Here, you can see that now these rays are diverging. So all you need to do is just sort of like do the extrapolation, or you extend those rays just to figure out where should they cross. They could be an actual crossing, or they could be like a virtual crossing. But in this case, it's clear. This ray of light is diverging. They're never going to cross. So that means you have to extrapolate back. And that's where your position of the image is. So in this case, because of the law of the reflection, the image distance P and the object distance P and the image distance I are going to be exactly the same. Cool?
Okay.
That's simple. All right, now things gonna get more interesting here. What if the mirror is curved? That's what we want. All right, so let me sort of introduce to you some terminology, and then we're gonna take a break. Sounds like a good plan? Okay, so what we have over here is things get more interesting when you have a curved mirror. Okay. Oh, there's a question: mirror reflect 100% of light. I would say not. Oh, no need to clap there. It's almost, let me say, almost. All right. So I would say we are going to find a very hard time to build a perfect 100% mirror. There's always some factor that you lose some reflection, or you lose something, right? But you can get very close to 100%, right? But in theory, we assume that the reflection is 100%. Okay. All right. So I'm just thinking in reality, yeah, you always lose something. Yeah. Okay. Now, what we have in a curved mirror over here, you have a curve in such a way that if you send in the light that is just a parallel light, so the easiest way to think of parallel light is just the laser beam. That's the easy one. So you can send in the light. Now I can trace two rays once again. If these two rays are just horizontal rays, then the reflection, we're going to pick the curve that give you a curve of a spherical. So that means what we're looking at is a spherical mirror. The reason that we pick a spherical one is because when you send in the light in a parallel direction to the central axis over here, the reflection is going to get through a single point right there. Okay. And the second thing that you know right away, every time that you draw a line perpendicular to a circle, that line eventually going to get to the center of the circle. Okay. Does that make sense? Right? Because that is the radial line. So that means that normal, the one that we familiar with, the line that you draw perpendicular to the interface or perpendicular to the surface of the material, eventually is going to go through the center of curvature. Cool. And because of the law of the reflection, you say the incident and the reflected beam has to share the same angle. So that means the distance that this ray is going to cut, the distance at the central axis is going to be half of the distance from the center of curvature. Does that make sense?
Okay.
Okay, so that means if you know that this distance from point C to the center of the sphere is the radius of this curvature, so you know right away that the distance from here, the point of crossing to the center of the mirror is going to be half of that. Yeah, from the law of reflection. And because this is going to be the point where the ray of light crossing, so we're going to call this a focal point. And the distance of this focal point to the center of the mirror, we're going to call it focal length. So that's F right there is your focal length there. Okay, let me highlight. Okay, so it's going to be a little bit better. There you go. The F over here you're looking at, that is your focal length. There you go. Does that make sense? All right. And the center of curvature C is showing up right there. Okay. And the one that is already messed up there, that capital F there, that is your focal point. Cool. All right. So same thing will happen on the right side if the mirror is curved backward. So in this case, you have a diverging case. The reason it's diverging is because once again, if I send in a horizontal ray of light, now the reflected beam is going to bounce off using the same law of reflection. There's nothing different. Okay. And once again, that line that you draw perpendicular to the surface is going to eventually, oh, so bad. So why don't I use this better? Sorry, guys. It just sometimes just forgot that I can just draw better with this. There you go. Here we go. See, the figure, it doesn't work. Oh no. See, you know, sometimes textbook doesn't really draw everything in scale. Oh, maybe it's my bad. Here we go. There we go. That's good. Almost. There you go. This may be my bad. Oh, okay, I know. I should go backward here. All right, guys. So I have to draw. Here we go. I think that's better. There. That's the normal line right there. Here we go. Okay, so the normal line there will just go through the center of curvature C. And of course, if you extend your reflected beam, you are going to get to the focal point here, because if you do in a symmetric way underneath, that's where these two lines or two rays is going to virtually cross right there. Cool. All right. So once again, you're going to still call this distance over here the focal length. Okay. And the distance that is a radius of curvature, that is your R, the radius of curvature right there. Cool. All right. That's it. So in conclusion, oh, I used the capital R for the radius, I think. Sorry, guys, but I hope it's not confused you there. Okay, it just small r. Just keep going back and forth there. Small r, there you go. Okay, so conclusion, if you have a spherical mirrors, okay, you will have the center of curvature, no problem in both cases. Okay, and half of that radius will give you the focal length. So the focal length is half the radius, all right? Plus, you have two choices to make, okay? I mean, you have two types of mirrors to choose. Ones that have the focal length in the front, the figure case, the figure on the left. If it's curved like this, you can call this one a converging mirror because it's trying to converge light into a single point. Or you can have the focal point behind the mirror when it's curved in the opposite direction, that's on the right figure. You can call this a diverging mirror because it's diverging the light out and is virtually crossed at the virtual focus, which is behind the mirror. Okay. The one on the left, you can call it a concave mirror. The one on the right, you can call it a convex mirror. But to me, it might get confused sometimes that, I mean, well, it's not that bad, but concave, it means it's concave, it's kind of sort of like curve away from you, and convex is like curve towards you. All right. But if just want to be clear, converging and diverging seems to be the easiest way to sort of distinguish between these two types of mirrors. All right, cool, guys. So I think we got the terminologies down. So we're going to have to deal with the focal length, and we know it's half the radius of curvature, and we know what is going to be the image distance, object distance, and after the break, we'll figure out how can we figure out the image that is being formed from the spherical mirrors. Okay. In the case of the flat mirror, it's easy, but what happens to the curved mirror? All right. That's after the break. Okay.
Okay.
Let's talk about how can we actually determine the type of image and where is going to be the image location from the curved mirror. Okay. So it turns out one way of doing this, it's kind of like, okay, don't have to do any calculation, just use the geometry that come directly from the law of reflection. Okay, so let's take a look at this. For example, if you know how things go at the mirror, which is just a purely reflection, right? So that means right at the point of contact here, you can draw the normal line all the time. That's your normal line there. Okay, and every time that you have this, you always have like the incident angle equal to the reflected angle, incident angle equal to the reflected angle, or not that mini angle there. Okay, so what you can do is just you trace curve, or I mean trace a line, because we know what will happen. For example, you can draw like this. Okay, and hit the mirror, it's going to reflect and like that. Something. Okay, cool. So now you know one ray is going to travel in that direction. So you pick another ray and then just pick an easy one. When I say easy one, mean you just pick the one that actually when it's reflect back, is reflect horizontally. And once you do this too, you know where these two rays are going to cross. It's going to be right here. That's a crossing point, and that's it. Because these crossing points are from the real rays crossing. So we can conclude that this is a real image. Does that make sense? Okay, so that's how you pretty much figure out where the light should go. And are they going to cross at some point? If they are, and they are actually crossing, you're going to get a real image there. Okay, so this one actually will not stop you from picking any other point. But the reason that I picked these two rays, because it's easy to draw. For example, if you're a can I draw some other rays that's pointing in different direction? Well, yeah, you can. You can go here, and then you have to do that reflection thing, which is you have to draw the normal line there, and then eventually the reflected beam is going to come down here. So does that make sense to you? All right, so you can do as many rays as you like. They are all going to cross at the same point. That is guaranteed that that point must be the point of image location. Cool. All right, so that's what it is. But in reality, I mean, no one, I mean, of course you can, but draw this kind of like lines and do the reflection, you have to measure the angle. It won't work by hand. It might work with the software, but it won't work using pens and pencil. All right, you might do this like back in the day, but we're not going to do it here. So what can we do to figure out the location of the image? It's just by some relationship between, you know, the distances and all the stuff. So I'm going to give you the equation a little bit later. But the point that I'm going to make later next is this. If you notice, the original height of this object is this high. But if you look at the location and the point that the ray crossing is just only crossing at this point, which is, you can see that it's shortened. So that means your image is going to have a reduced size. So you have the reduction in size of the image. So you're going to get a smaller image in comparison to the object itself. Okay, so that's one thing. Second thing is, you can see that now, because you mapping the tip of your object, and the tip of the object shows up at point E down there at the blue dot. So that means your image is going to flip upside down as well. So this is going to be the case of this one here is, if you place an object in front of the concave mirror, and if your object is quite far away in this case, you are going to see the inverted image with a reduction in size. So you're going to have the inverted image that looks smaller than the actual object. Does that make sense? All right. So this is something that you can, I mean, it might not be able to see easily, but if you think in reverse though, if you think in reverse, I mean, maybe the condition that you probably see in, well, might not be everyday lives, but if you ever use this, I don't know how to call this properly, but I think this is like the cosmetic, I don't know, like makeup mirror or whatever. It's like blow up your face so huge. And that because when you put your face so close, now you switch the role between the object and image. So you can imagine that you place your face right here. So now your face just showing up here. So now this is all objects, okay? And then because of the light travel in a straight line, you can reverse all the ray and everything, just go back. And then you're gonna have this as your image instead. Does that make sense? Okay, so I mean, you can always switch the position between object and image because everything will be connected through the law of reflection. Nothing has changed. So that means if you put your face here, you should see something bigger. Well, this is not the case, right? I mean, I'm just saying. You have to put yourself closer. So you're supposed to stand here, right? And if you do the calculation here, what you're going to get at the end, it's going to be, I mean, this, how can I say, this location is different from the one that you see on the right. That's what I'm saying. So if you place your objects here, then your image will show up larger on the back, but the image is not going to be inverted. That's what I'm saying. But because, do I have the, no, I don't. So sorry, guys. I just thinking of, I mean, I thought, well, it will be easier to see here, but might not be. We might be better to just use simulation again. But anyway, that's later. But the point is, the concave mirror, the one that you might be able to use before, was just from that sort of like the makeup mirror over there that blow up, enlarge your face, and then you can sort of like deal with your face a little bit easier. Right there. Okay. On the other hand, there will be a convex mirror. And in that case, you do the same thing. Okay, you trace the ray of light, and you can see that in this case, if you follow any rays, and this one, we just pick the easiest two that we can draw. And it turns out at the end, you get the image behind the mirror. Once the image is behind, so that means the point of intersection is behind the mirror, you can guarantee this one is going to be virtual image because light can never travel behind the mirror. And one thing that you can notice over here is the size of the image is going to be smaller, but it's still upright. And this scenario is the one that you saw from the street corner when you have this convex mirror, like huge one that allow you to see the other side of the corner there. But if you look at the image that shows up on the in the mirror, then you can see that the size is going to be smaller, but it's still right side up. Okay. Cool. All right. That's what pretty much things that you can notice around you. Now, here comes the calculation. So because we're not going to do the ray tracing like this, it's going to take you time for you to do. So what we are going to do is this. We're going to use the equation, okay? But before we get to that, we just have to do some agreement on that because we already saw that you might have the enlargement or reduction in size. So the easiest one that you can define that is just through some magnification factor. And that's easy. You just take the image size divided by object size, and that's it, you're done. And in this case, because we do everything in one dimension, you might just have the height of the image divided by the height of the object. You get the magnification. Okay, so we call that the M. But then I would like to sort of ask you to sort of like do this formula with a sign. So this one, I put an absolute sign there because if you just want to know, is it going to be an enlarged or is it going to be reduced in size? But it turns out, if you memorize this formula with a negative sign in the front, it will help you later that I will show you. If the M is positive, you have an upright image. If the M that you calculate has a negative value, it's going to represent an inverted image. So I think it's good to take this formula instead just taking just an absolute value. Plus, the second thing is, the nice thing about this ratio over here is the ratio of the size of the object and the image turns out to be the same ratio as the image and object distance. So that means I can replace the image size with the image distance, and I can replace the object size by the object distance. Okay, and in some textbook, they use P and Q. This is confusing, right? And in some textbook, they use like S and S prime. So, and in some textbooks, they use like U and V. There are so many terminology to use. So that's why I just throw them in the mix over here, just so you get used to many sort of names that you can use. Okay, so I and P, image and object. It could be Q over P, it could be S prime over S, it could be V over U, same thing. All right, they're all good. Okay, a little bit confusing, but I hope it's fine. It's just, just the naming stuff. All right, guys, here comes the main equation, and it's right here.
Okay.
Welcome mirror equation. And it's simple. It's just a pure algebra. It's 1 over P plus 1 over Q equal to 1 over F. You are done. That's it, guys. Okay, so that means it's just saying that the inverse of the object distance plus the inverse of the image distance must be equal to the inverse of the focal length of that mirror. Isn't that nice? Okay, so what we have over here is now, I think this is the important stuff, all right? And I want to talk about this one once. And if you understand how the mirror works, you will understand lenses right away, right? Without any problems, okay? So let's do this. So the way that I treat this equation is like this. The most complex portion of this utilization of this equation is the sign. You either have to pick the positive or the negative one. How do you pick that one? It's by looking at the nature of the light, where light goes. That's it. That's what we want to figure out. So start with this. So when you have this equation, okay, and you're looking at, let me highlight this one, P, that's an object. As long as you have a single mirror over here, the object will always stay in the front, right? Does that make sense? So that means you can say that object right there always positive when the object is in front of the mirror. That's what it is. That's positive, which is fine. I mean, as long as you have a single mirror, it's always positive. Now, turn our attention to the image. When you look at the image, light has to reflect off of mirror. So that means the only way that you're going to get the real image, it means everything has to show up in the front of the mirror. Does that make sense? Because if something shows up in the back, or it means the image shows up in the back of the mirror, we already saw ourselves in the mirror in the bathroom, that's a virtual image. So that's what I'm going to conclude, that for image, whatever come in the front must be positive, because where the light has to go. Light has to go back from the reflection. So light has to stay in front of the mirror. Does that make sense? And whatever that shows up behind the mirror, that will take the negative sign. And that's the reason why I can conclude that the focal length of the concave mirror or the converging mirror is positive. With me, guys? Because see, the focal length is in the front. And the focal length is the the length that determines the image. So whatever related to the image, it's going to be positive when it's in the front. And in contrast to that, the diverging mirror has everything. See this? Okay, let me use different color here. See, it shows up in the back. See that? So everything that shows up in the back, we're going to call it the negative portion of this. So this is the reason why the focal length of the diverging mirror, that's going to be negative sign. And anything that shows up in the back is going to be virtual. That's it. That's the only key things that you need to apply this equation. And by understanding this side, which side is positive side, which side is negative side, well, you don't have to worry about this table at all. I don't know would that work or not, but it seems to me that's easier to just make sense of where light go. Okay, light has to appear in the front to be real. Light cannot travel into the back of the mirror anyway. So if the image shows up in the back, it must be a virtual image. Cool. All right, let's give it a shot and see how it goes. All right, it will be better to look at an example. And once you understand this one, lens is done. Okay, which is the next one. All right, look at the concave spherical mirror. So when you have a concave one, so it means you're trying to look at the focal point that is positive. So the curvature, I mean, along with the focal point, it's looking at in the front of the mirror and everything. So over here, you get the R to be 20 centimeter. So that leads you to the focal length to be half of that. That's 10 centimeter. And the good thing, I mean, just to be sure, don't forget, it's going to be positive because it's a concave mirror. With me, guys? Okay, that's good. There, it's positive because the focal length and focal point is in the front. Next, find the location of the image for object distances of 40, 20, and 10. For each case, state whether the image is real or virtual, upright, inverted, magnifications, everything. But you'll see that it will be done in two equations. All right, we have only two equations, 1 over P plus 1 over Q equal to 1 over F. That's mirror equations. Let me call it the equation number 1 here. And the second equation that we use is M, magnification, is just negative Q over P. That's my second equation that I need. I need only these two. All right, let's give it a shot here, guys. So I got the F done here. What about the P? For part A, P is just 40 centimeter. And because you have only single mirror, it's going to be positive object distance because object is real object. I mean, you have an object in the front, yeah? And that's it, guys. Plug it in into your mirror equation, 1 over positive 40 plus 1 over Q. The Q, that's the one you want. That's your image distance, equal to 1 over F, which is plus 10. You don't need to convert the units as long as you use the same units in all three parameters over here. So I'll keep the centimeter units here. So what I have here is, now you're going to get 1 over Q equal to 1 over 10 minus 1 over 40. And that is just 3 over 40. And that means Q is 40 over 3. Cool.
Okay.
Now, see this? This equation gives you a positive value. Let me emphasize, this is positive. So what does it mean? It means if I draw a figure over here, yeah, all right. So my focal point is 20, and my radius is, I mean, my object is at 40. That's where my object here. Because you have a positive 30.3 to be your image. So that means your Q has to be in the front because it's real now. It's positive. And 40 over 3, this is about what, 13 something. So it's going to be somewhere here. That is your Q. Does that make sense now?
Okay.
Okay, positive means it's in the front. Now, next, now you know where your image is. Now let's figure out what type of image it's going to be. But John, it's positive. So this must be real. With me, guys? So far, so good? Now, once you know the type of the image, let's take a look at the magnification and the orientation. Now let's try the second equation, the M equal to negative Q over P. Plug in everything that you have already calculated. Q is 40 over 3. P is 20, is that right? 40, sorry. P is 40. Okay, so over here, what you get is just, oops, sorry, my hand. So what you get over here is just negative 1/3. See the negative sign there? Okay, so the negative sign there is just saying that your image is inverted. 1/3 is just a number saying that it's going to be 1/3 in size. So you get a reduction in image size. So what you have over here is, let me emphasize on this. The conclusion is this now. Your object is right here at 40 centimeter. Okay, let's say it's this tall. At the end, you get your image right here, but still in the front, and it's still real, but it's inverted and it's only 1/3 in size. There you go. Let me draw it smaller one. It's done. Woohoo.
Okay.
So you know how to apply these two equations now? All right. And the scenario that you're seeing over here, this is exactly what you saw back here. See, when you have an object far away, okay, and then you try to figure out the image, it turns out the image is in the front, inverted, reduction in size. Cool. All right, try again. Part B, pretty much the same. Now you just have different value of P. P is positive 20 centimeter. Plug it in into your equation, 1 over P plus 1 over Q, the one you want to figure out, equal to 1 over F. Okay, if you want to emphasize positive sign is good. So what you have over here is your 1 over Q is going to be 1 over 10 minus 1 over 20, and that will give you 1 over 20. Isn't that nice? Okay. And what you have over here is still positive, which is fine. Okay, you still have positive. So that means you can say the positive of this one means you're going to get a real image. What about the magnification? You take M to be negative Q over P. The Q you just already calculated, it's 1 over 20. Sorry, have to flip upside down too, my bad. Okay, guys, sorry, 20 over here. Don't forget this is 1 over Q equal to 1 over 20. So the Q has to be 20, yeah? Don't forget that one. Sorry, my bad. It just ran out of space, so I forgot to flip it upside down. There you go. All right, but positive sign mean is real. That's real. Okay, divided by P. P is also 20. Oh, that's good. That's just negative 1. What does it mean? It means for part B, you place your object at 20. That's your object now is being placed at 20. Now you get the image at exactly 20. Is that cool? So your image is just exactly at 20. And it's upside down because it's negative, but there's no magnification or reduction because M is equal to 1. The magnitude of M is 1. So you get exact same size of the object. So what you're getting over here is, here we go. Your image is standing at exactly the same location as the object, but it's just upside down. And this one makes sense. Why? Because you are standing where? At 20 centimeter, and where you are? Right at the center of curvature. You guys with me? Or twice the focal length. So when you are standing at the center of curvature, what you have is just light will just hit the mirror and just reflect back to you. That's it, because you're at the center of the sphere. However, because of the reflection, everything gets flipped. That's why you get an inverted image, but there'll be no magnification. There'll be no reduction in size because it's just a pure reflection. That's it. Isn't that cool?
Okay.
I don't know if you call it cool or not, but that's what it is. Now you can imagine what happened to part C now. Part C, the image location is now at 10 centimeter. You can put positive sign in there just to emphasize. And then from the mirror equations, you're going to get 1 over P plus 1 over Q equal to 1 over F. Now, this is going to be the weird one because you get a cancellation. So 1 over Q is 0 or Q is at infinity. But that's no big deal because in part C, you are standing right at the focal point. And then you already saw that whenever things that's at the focal point, the light will just hit the mirror and get out in the parallel direction. You guys remember this back in the day that we, back in the figure that we introduced this whole mirror business over here is, if you have a ray that come in parallel to the central axis, just like horizontal axis, it will just bounce off and hit the focal point. So everything can be reversed. I already told you that. So I can go backward. So if I start from the focal point, light will just travel backward. So it will go to infinity. So there's no doubt. This equation gives you that. So if you're standing right at your focal point, then the light will reflect and travel to infinity. So that's why you say the image will just doesn't show up. You get a parallel line, like a parallel beam out of it. So image will show up at infinity. Sounds good?
Okay.
So I hope by showing you this, I think it's just how simple it is to sort of like, apply this mirror equation along with the magnification equation, and then you can solve everything. It's done. All right, so what I can do next is now sort of summarize what will happen. This is the last part of this lecture now, and I hope it will be much easier. What happens when now you turn your attention to lenses? So instead of have a mirror to reflect things, you have lenses that can let the light through. It's just a transparent material. Like for those of you that wearing glasses, that lens in front of your eyes there, that's the one that lets the light through. But because the light has to go through this material that made the lens, it's going to get refracted. Does that make sense? It's get refracted instead of reflected. But if you think logically, if you make the lens curve, okay, so you have some sort of like curved lens, you're going to go through two refraction, which is, I don't have to worry at this point. I mean, that's fine, John. You're going to, refract here, refract that. I don't care. Once you get that refraction, it turns out if you can make it like a focal point, just you saw in the mirror. So that means when you hit this lens with a parallel beam, horizontal beam, and after the refraction, it's meet at a single point. You can still call this one a focal point, just like before. This is your focal point. And the distance of the focal point to the center of the lens, you can still call it the focal length. Does that make sense? But the only thing that looks different now is that whatever things that happens must happen after the lens. Isn't that cool?
Okay.
Make sense now? So if I'm going to use this sort of like highlighting here, you saw that the blue region over here, this is where the light should go, right? In the case of the mirror. So what kind of blue region is supposed to happen here in the case of the lens? Well, Ajahn, it's supposed to come out here. That's where the light should go, because light can never get reflected back into the front of the lens, even though, okay, partially get some reflection, of course, but not here. So what you have over here is now for the lens, the only thing that you have to flip your brain around is just saying that things we're going to get real when things happens behind the lens. So the image will be real when it's behind the lens. So you set the positive sign to be behind the lens. Anything that comes in front of the lens in terms of imaging, anything that related to the image and it's related to the front side of the lens, that will be your negative side of the image. Is that cool? All right. And that's the reason why by using the same logic over here, we can call this left lens to be a converging lens. Converging lens. And you can guess right away, because your focal point is behind the lens, and that's where the positive side of the image is supposed to be, the converging lens will have a positive focal length. Cool.
Okay.
Now look at another type of the curvature. If you have a diverging lens, so that means when you send in the light get diverged out, diverged out. Of course, they're never going to cross. So the only way that you can get the crossing point, you have to extend those rays by yourself. So now you get a virtual crossing of those rays. And now you can look at this one. If you look at the distance, now your focal length shows up in the front. And the front side is the one that we say, hey, John, that is your negative side of thing. That's the front. Light shouldn't be here anymore. It's supposed to penetrate through and send out to the other side of the lens. So that's why you can say that this type of the lens, the focal point is going to be negative. Isn't that cool?
Okay.
And all the logic about the lens and the mirror will be exactly the same. The only thing is you just flip the location of the positive image to be behind the lens. The mirror is in the front, lens is in the back. That's it. Everything else stays the same. All right. Before we get into the equation to use, I mean, when you say the converging lens, you means that the center of the lens will be thicker than the rim. That's all. If you have this condition, then you always have a converging lens. Okay. So this is good. It's thicker, it's thicker, it's thicker in comparison to the rim. So these are all converging lens. Okay. It doesn't have to be exactly just only this figure over here. Same thing with the diverging lens. As long as the center is thinner than the rim, okay, that is good. These are all have the property of diverging light. And for those of you that have the short-sighted glasses over here, then that's they are all using, I think, this type right here. Okay, it's diverging lens, but it doesn't look this bad, right? Because when we do in, like, you know, every time we use a representative of diverging lens, we always use this figure over here. But in the actual glasses, it's also diverging lens, but it's gonna look really bad if it's made out of this shape. So usually it will be, it's the convex concave. That's what it is. It's like convex and concave, but the center is thinner than the rim. That's what it is. All right, guys, let's give it a shot. How can we calculate the locations of this, of that? What type of image you're gonna get? Inverted, real? No, well, no problem. You can do it using the ray tracing, just like before. But you kind of know, like, okay, we're not gonna do that by hand, all right? But we kind of know, like, we can always do exactly the same as the mirror, but instead of reflection, you do the refraction. Okay, but the way that we're gonna do it, we're just gonna use the same two equation again in our calculations. So you look at this one, and then does it look familiar to you?
Okay.
And that's it, guys. It's still the same exact equation. And we call this thin lens equation. It's just like mirror equation, right? And the reason for thin is because we're going to assume that the two interfaces over here that try to help you bend the light into a focal point over here seem to be pretty close to each other. So you don't have to worry about the thickness of the lens, all right? That will be like complicated problems talking about, hey, what will happen to the thick lens? Okay, and then you have to do the refraction on the left side, and then you have to do the refraction on the right side, and then you come up with another kind of equation to solve. But let's start from a simple one. Let's say, hey, lens is so thin that you don't have to worry about the thickness of the lens. So let's call thin lens equation. So it looks the same. You have the object distance, image distance, and the focal length, exactly the same, except now the image will be positive when it's behind the lens. Okay, the second equation use exactly the same. To find the magnification, keep the negative sign there, just to be nice. And then you take the ratio between the image distance and the object distance. The interpretation stay the same. If M is positive, means it's upright. If M is negative, it's inverted. And if the value of M is larger than 1, you get an enlarged image. If M is less than 1, then you get a reduced size image. Cool. All right. So
Okay.
that's kind of nice and neat. to be able to do two things using the same sets of equations. Let's dive into it, shall we? All right, almost done, guys. Stick with me here. An object is located 20 centimeters to the left of a diverging lens, having a focal length given. Determine the location, magnification. Actually, we should be able to determine everything about the image, right? So let's start with this. Okay, the location of the object is always positive because we have a single lens here. So that is 20 centimeter there. To the left of a diverging lens. So if I want to draw some sort of like a diagram, diverging lens look like that. Okay, and the focal length of that diverging lens is given, but then we already see that, oh, diverging, the focal point is in the front, and the front one is the bad one, right? It's a negative one. So just to guarantee that the focal length of this diverging lens is negative. Cool. All right. So what we have there is now we can figure out the location. So part A, applying the first equation, thin lens equation, 1 over P plus 1 over Q equal to 1 over F. So 1 over P, it's always positive in this case, single object. The Q, the image location, that's what you want to figure out. And the focal length over here is negative 32. You don't have to convert the units once again, as long as you keep the centimeter units, all three terms. Okay, so there's a question comes in before. Okay, you guys can solve this one. 1 over Q equal to now negative 1 over 32 minus 1 over 20. Oh, now it starts to look like you're going to get a negative outcome here. Negative outcome. All right, so what you have here is Q is going to be, now I can do the, all right, you guys probably can do better algebra than mine, but it's going to be like what, 52 here with the negative sign. There you go. There. All right. You can cross this and that, but I'm gonna just leave it there. So let's say what I'm saying over here is now you get a negative image distance. So what does it mean? It means your focal length is probably, let me put 32 here. That's 32. Oh, let me put a bigger scale here just so it's easier to see. Okay. Give me a second here. All right. So let me put focal length here. Okay, let me put there. That's 32. Okay. And now your object, it's already only at 20. So let me try to draw everything in scale a little bit. So your object is actually is pretty good already. Yeah. Yeah. That's your object is right there. That is your 20. There you go. So now what is the final answer over here? This numbers is how much is this? 600 something. So let me call it like 12-ish. Is it good? Yeah. All right. So that means you're gonna get your image shows up somewhere here at the cross, 12-ish, but it's negative. So it means it's in the front. It's not gonna go in the back. And because of that negative sign right there, it's going to be virtual. It shows up in the front. Cool. All right. Now, what we have next is try the second equation there. The magnification equation is negative Q over P. So I just take the whole Q over here along with the sign right there. So it's going to be negative 32 times 20 over 52. I don't want to use approximate 12 just in case I made some mistakes there. Divided by the object distance, which is 20 right there. Okay, the good thing is I can cancel 20 out. And as you can see, negative sign turn positive. So it's going to be positive 32 over 52. Yeah, cool. So what I'm saying over here is now your final image will be upright because it's positive M. Plus, because this one is less than 1, so it means you're going to have some reduction in size. So that's what you get right here. There. With me, guys? So it's going to show up at 12, around 12, approximately 12 in front of the lens. And it's going to be reduction in size. The ratio of the size is going to be that 32 over 52. And it's still upright. And you are done.
Okay.
All right. So as you can see, the way that you apply these two equations are exactly the same among mirror and lenses. Everything looks exactly the same. The only thing that you have to make sure that you understand how to apply is the sign. And once you take that logic over there, it's very simple. Where the light should go. For the mirror, light should get reflected, so everything is positive in front of the mirror for the image. For the lenses, the light's supposed to penetrate through the other side of the lenses, so the image supposed to show up behind the mirror. I'm sorry, behind the lens. So that is the positive side for the image. And once you have this one done, everything is all good.
Okay.
Okay, hold on, huh? Makes sense? All right. So there's a question here. So when we wear glasses with diverging lens, object will appear closer to our eyes. I will have this discussed next time. I think that's a very good question, and that's how to fix your sort of like disordered eyes. Okay, so that's, well, object will appear closer. Okay, maybe just different way of thinking, but it might not appear closer because we just want the image of the thing that you cannot see by your own eyes to appear at your retina so you can see it after the wearing the glasses. So I'm not so sure if that is going to be the answer, that the object will appear closer, because it might not appear closer. Otherwise, then I will have problem grabbing stuff if the object appear closer than it's supposed to be, right? But I'm still fine. Looking at stuff, I can sort of still realize where things are, like close, far, and you know. All right, so I'll explain that next time. All right, along with you don't understand how classes work. Okay, so I will explain the internal, so like all the underlying physics behind correcting your sighting, okay, of your eyes. That's next time. Along with, we will answer what will happen if we have multiple lenses or multiple devices that do multiple things. What can we still extend our formulas to? Okay, guys. So that is it for today, and then I'll see you guys on Saturday. Yeah. Okay. Take care, guys. Okay. See ya.